Good morning, everyone. Welcome to our presentation. So, in the morning, we listen maybe 2, 3 industry talk. So this is going to be a kind of a bit academic talk. And yeah, I'm used to when I take the class, I see a couple of seats are vacant. So it's always happen. So it's the same here as well. Okay, so in this presentation, we basically talk about the federated learning and scheme is privacy and security. So here is the outline of our presentation. We divide the presentation into group. In first part, I will try to give you a bit overview about the federated learning. Maybe it's the new concept for some of you. So after then, we'll talk about our contribution in this area. And if we have the times, then we'll take few questions from you. So that's the plan. So I think all of us are familiar with the traditional machine learning, right? So most of you use that traditional machine learning model that you collect all the data in a central server, and then you train the model based on that data, and you have a model. So most of the case, you can expect that that model will be generalized model, and you can deploy the model as a service to provide the service to the different clients. So this is the traditional setup, but it has some problem. A few problems. So one of them, let's say the data privacy. So we'll bring all the data to a central server. So if we share the data to a central server, if the server is compromised, maybe there is a privacy issue. And there is one new dimensions that we see. This is the regulatory concern that you cannot share your data outside a geographic boundary. So in that concerns, you may not have the settings where you will be able to share all the data to a central server. And even if you have a large set of data, so you are in the big data age, so we have a lot of data, we need to transfer a lot of data, so it's also not that cost efficient. So there is a new technique that we call it federated learning. So it's basically, let's say that the client or the parties, let's say in this case, it can be a hospital. So that's the best example. They can keep their data locally and train their model based on that local data. And then they share the model update, not the data, with the server. And there is a cooperation between server and the client. So after a couple of round of training, so the server as well as the client all will have a generalized global model. We call it as a global model. If the parties train the model, then we call it local model. So we will have the local model, and by using the local model, we aggregate it and then have the generalized global model. So that's the general idea of the federated learning. So the one of the important role in the federated learning training is one of the algorithm that we call the aggregation algorithm. So we have the server side. So server actually get all the weight or all the gradients from the client. So there is the challenge that how you're gonna combine those weight and then let's say they mash them together and assign them to a model. So there are two classic algorithm that widely used. One is the Fed-ABG and another was its SGD versions. But the idea is simple, that you have all the weight from the local model, users averaging them together, and then you have a combined weight, and you transfer it to the client. So it's gonna happen couple of rounds. I'm not talking too details about this, the mathematical concepts. So that's actually happen couple of rounds, and after then we have the expectation that we'll have a generalized global model. So Yeah, there is frameworks and applications. So can you talk a bit about it?
Hello. Thank you, Professor Morshedul, for the comprehensive review on federated learning. So now that we know what federated learning is, let's look at what open source frameworks there are so that we can actually use it. Probably the most popular one is TFF, which is a short form for TensorFlow Federated. It is used by Google for next word prediction and emoji prediction. If you use Google's Gboard, this is the one they use. Next, we have Fate, which is, I believe, developed by a company called WeBank. It is a decentralized federated learning framework, so it's not the usual client-server one. Instead, it's a peer-to-peer one. It has built-in security features like differential privacy, so it's mostly used for financial transaction and for data that needs that extra layer of security. The next one is IBM's framework, IBM FL. They famously use it for predicting the geographical outcome of COVID-19. The next we have OpenFL, PySwift, and Leaf, which have seen a lot of improvements, which have seen a lot of use cases in convolution neural networks. So they are mostly used in CNN domains.
Okay, so if we talk about the application of the federated learning, you see that there are a lot of different applications, but most of the case we can see it. Healthcare is one of the main domain because they have some regulatory restriction not to share the data. So IoT is the another domain, and the finance. So we can use the federated learning in those domain. So, I mean, when we see, we focus on the challenge in the federated learning, we can see all the problem in three different perspectives. So some of those problems that are directly related with the machine learning related. Let's say most of the federated learning, they actually use the deep neural network, but there is an options to use the classical machine learning model to do the federated learning, and based on the data distributions, there are different ways that the data are distributed. So we can divide that one in horizontal, vertical, and there is one thing that when we train a global model, that single model cannot fit for all the clients. So in that case, there is a concept that we call the personalized learning. So let's talk a bit details about the issue that are related with the the machine learning perspective. So this is simple, the way that I discussed before, how to train a federated learning. So we can use our traditional machine learning model to train the federated learning. In that case, we'll have the input X, let's say, and Y is the output or predictions. So we will have a linear model. So our assumption is that to fit a linear model, that locally, and then share the weight and bias with the server, and server will get those weight and bias and combine them together and send it back to the client for the next update. So the similar way that it also have the two version. One is the weight and bias version, or is also have the HCD version as well for the aggregations. So this is one of the interesting way to do the federated learning. The way that we see the training of the federated learning, so it's traditionally the horizontal federated learning because the data is partitioned in horizontally. Let's say if I am a client, I have all the features, and I have the data from the couple of client or couple of classes. So in that case, I will train my own model by using my data as a local client and share it with the server. But let's say if the data is not distributed horizontally, if there is another way that data can be distributed that we call the vertical. Let's say that I don't have all the feature of a particular client. I have a subset of features, another client have the other subset of features. Maybe I don't have the level of that particular client. Okay, other client have that level of client. So anyhow, we need to combine these two data set together or logically so that we can together train general global model. So that is why we see this type of, the data dividation, we call it as a vertical partitioning. And to train a federated learning in the vertical partitioning is a bit tricky. As I said, that there is one of the steps that we need to be ensured, that is called the private site interaction. Anyhow, me and my other client, we need to have a kind of interactions to not merging the data together. We can keep the data in our local devices, but still we can assign a logical identity of that data. Let's say that this is the ID1 for my data, and this is the ID1 for his data as well. So just assign a logical ID, and then share that ID with the server. So if you share that ID with the server, you see at the top, so the problem will be straightforward. So in this case, we just use our own model. It can be a single model, or it can be a part of the model. We just will do the forward pass based on the data to train that particular part of the model. And then when server get the features or the vector for this from this forward pass, he will this vector as well as the label to train the model, and will get the loss from that one. And then he will do the backward pass from top to bottom. So it will be run couple of round. Then at the very end, everyone will have a generalized global model. It's simple and straightforward, just logically combine the data. So then the personalized federated learning model.
Okay. Now that we have established that federated learning is a pretty straightforward framework of doing machine learning, you basically have clients sending their weights and biases to a global server. The global server aggregates those biases and creates a global model, and it sends that model back to the clients, and this process goes on. So what is personalized FL? I like to think of personalized FL as a solution to a problem in federated learning. The problem is that each of the clients have unique distribution of data. What we call by that is non-IID data. So basically, this difference in distribution comes to the fact that some clients might be missing some classes of data, while other clients might have more of those data sets of those classes. Picture a data sets having 4 classes. Let's say client 1 might not have any data examples of class 4, but they might have a lot of data of class 1, 2, and 3. However, another client, say client number 13, he might only have a few examples of class 1, but not enough so that the model can generalize. So personalized FL tries to fix this issue by making sure that most of the clients roughly have the same distribution of data in them. So the first tactic that we can use is something known as data augmentation. It's just a fancy word of saying that, say a client, if a client does not have enough data samples for a class, what we can do is we can take the pre-existing data of that class, we can apply some transformations on that data, like say if it's an image data, we can change the pixel values, we can do some rotation, some scaling, and create new data sets, create new data examples for that class. So that's what basically data augmentation is. Next is a term called regularization. Regularization is a tactic used in traditional machine learning to make sure that the model's weights do not get very high and that the model does not overfit. It is basically to make the model as general as possible. In federated learning as well, we can do it very easily by appending a new term to the cost function. So the cost function plus we append the global model's weights and the local model's weight to make sure that the local models don't overshoot and overfit on its own data. We have some other concepts as well, like client clustering, which is to train clients with similar data sets together. So it's a more specialized towards federated learning. We have some other smaller concepts like meta learning, multitask learning, and distillation, which we'll be talking about more in the coming slides.
Okay, so it's about the personalized learning. So if I give you an example, let's say that biometric authentication. So in the biometric authentication, everyone have his own biometric data. So it's a single class data. We call sometimes it's a positive class problem. So if you have your own data and you use that data to train your model as a local model, so it will basically can decide based on your data. It never see the other data. So when you move that data to the server, move that model weight to the server, it just get the view of your data. When others model will come and then you will combine them together, it will not give you the good performance because all of the model are basically bias on their own data. So you will not have a generalized global model. So this is one way that we can define the non-IIDness of the machine learning, but there are some other examples as well. So some cases even when we talk about the personalized learning, we see that the scarcity of the data, maybe client may not have the sufficient data, how we can give the clients or how the client can get enough data to train that federated learning. So there is one way, maybe the data augmentation, that is the easiest way to do a generative machine learning model to train, get more data set. And there is other approach that say the global data sharing. So the restriction is that not to share the data with the server, but they say that, okay, you can share the data with the server by privacy preserving way so that other client can have that data to use, and then later they use this data to train their local model. So there is one of the approach they said, that probabilistic approach, how to share the data with the server in the probabilistic way, and then client get those data so that they can use those data to train their model. And another one, he said that the regularization. So regularization concept is a bit straightforward here, that when you have a global model and you send back to the local client, so client use their data to update the model. In that case, maybe that model will be biased on that particular data. So you need to give a guarantee that the model at the local site that will not drift far from the global model. If your single update drift far from the global model, when you get those model and combine them, you will get the different results. So there is a restriction that, okay, get the global model, but when you train, update the model a bit. So it's that baby step we call, so that they don't drift far away from the already trained global model. There are other personalized federated learning as well, but due to the time limitation, maybe let's talk about some issue from the security perspective. When you see the federated learning, we have the client, so this is the one side. Another side is the server, and another is the communications in between these two. So when you see the client side, there are different type of client. They have their own requirements. So maybe the model architecture will be different for the different client. Let's say I'm using the deep learning model, other one using the linear model, how we can combine them together to have a general global model. And obviously data distribution is the big issue in the federated learning. And the resource. So when you use the devices, some of the devices can be the IoT devices. So they don't have the enough resources to be part of the training process. So we need to consider that one as well. At the server side, there are not too many challenges. The main challenge is the aggregations, but still you need to be considered that if the server is not trusted, so in this case, there is a concept we call the secure aggregation, how we can do the secure aggregation at the server side. And obviously the communication is a big factor because not all the devices have the same bandwidth, and some device may be dropped due to their resource limitations. So there are a lot of communication issues that we can see in this area, but we'll not focus all of them. We'll focus some of those simple approach based on the client side and server side problems. Can you talk a bit about that?
So the FL architecture is loosely categorized into two types based on the types of clients that we're dealing with. So the first one is the cross-device FL. which is characterized by having a massive client population, but most of those clients are IoT devices or handheld devices like smartphones. We have a term heterogeneous devices, so it basically means that what kind of the device it is pretty ambiguous. As long as it has a processor, battery, memory, and it can talk through a network, it can participate in federated learning. There's a couple of challenges with cross-device FL. Just the fact that they are handheld devices, they are IoT devices. Clients may drop out during mid-training due to connectivity or battery issues. We have a concept of communication efficiency as well, because most of them are wireless devices, so they may not have the most fastest network bandwidth. So trying to send all the models' weights and parameters in every single update might be a bit heavy on the network. Next is system robustness. So we need to make sure that our FL is very robust and it can actually handle the dropouts and the partial updates coming from those clients. Privacy, of course, IoT devices, not all of them are very secure against cyber attacks. So we need to make sure that our FL architecture is secure in both the client side and the server side using tactics such as differential privacy and homomorphic encryption. So one of the examples of cross-device FL is the Google Gboard, which they use cross-device. So the opposite of that is cross-silo. So this is a much more reliable form of FL where we have a few clients, but those clients, like I said, are reliable. So they are large organizations like hospitals, banks, and research institutes. These participants, these clients are usually always online. And they have a very good system. So they have a good compute efficiency. They have good network, and like I said, they're very reliable. However, there are some challenges with this architecture as well, because the concept of data heterogeneity is also important. Again, since these clients are, let's take an example of hospitals. Hospitals might have a lot of data of a particular type of disease. So different hospitals see a different subset of patients, and those patients, we are not sure about the type of data, like if it is evenly divided into the diseases or not. So we need to make sure that the distribution of the data is made sure. Next is trust and governance. So these large organizations mostly have confidential data. So using these data for training machine learning models, there needs to be a kind of a legal framework and legal agreement that goes on in this case. So the example is like I gave of a hospital where a lot of hospitals throughout the country, they can train a model on the MRI images of their patients, and that model can detect the tumor or what kind of tumor it is by combining all the models from all these hospitals.
So we talk a lot about the data distribution. So this slide should come, that earlier, but you see that one of the paper that they did the experiment based on non-ID data 1 and 2. So this is the two different settings. They said that in non-ID data 1 setting, they said that each client will have the single class data, and non-ID 2 is that each client will have the two class of data. Then they try to train the model based on the well-known MNIST, CIFAR, and other data set. They have more than 10 class. So these two data, they have the 10 class, and other one maybe the 15 or something. So if the client only have one or two classes, so the performance reduce a lot. So this is the one form of non-IDness in the data distribution, but there are some other form as well. That let's say that I have a two class data, but some class I have too many sample, but for other classes maybe I have one or two sample. If we talk about the intrusion detection, we may have that type of scenario. So this is the one things that we can call it non-ID. And even we see the distribution of the feature. Let's say I'm a client, I'll have a feature, it have a particular distribution. Other client may have the different distributions. Even they might have the different level as well. And over the time, the feature maybe change their distribution. So there are a lot of different non-IDness, but we are dealing the first two. That's easy to deal, but there are some non-IDness as well. So then when we talk about the aggregation algorithm, they are not only two aggregation algorithm. We see that these are the two classical, but there are other. They are trying to focus on the different area. So let's say that first group basically they focus on the heterogeneity, data and resource heterogeneity. There are some algorithms that actually do the personalized federated learning. This is the time limitation, so we just show you what are the different algorithms that are available, knowledge distillations, and privacy preserving. So this is interesting. So there are a couple of algorithms that actually work at the server side to ensure the privacy of the data. One is the SecAgg. So this is one of the most popular one. Another is use the differential privacy with the aggregation, and another use the homomorphic. So that is our main interest, but recently there are some other recently published aggregation algorithm as well. So you may find maybe more than 20 aggregation algorithm in this area. So let's talk a bit about the privacy and security, because our main contribution is basically in this area. So we always see that in the federated learning, it have two main concerns. One is the privacy, another is the security. So, and obviously we need to be consider how to defend them. So there are different mechanism. So if we talk about the security issue, so most of the case that we call is manipulation attack that actually happen during the training. So you have the model weight and you are sending that weight to the server. So in the middle, maybe the attacker can manipulate that one to have his own advantage. So one of the attack is to create the backdoor, and another one, let's say that he would have interest to reduce the performance of the model. So we call that type of attack is the Byzantine attack. It can be one client or a group of clients can manipulate that weight, not to get a generalized federated learning model or global model. So this is the one directions that we can see the attack. Another attack is basically the privacy attack. We call it as an inference attack to infer the informations about the training data from the model training. So there are different type of inference attack that we see, and even we will talk about that one here as well. So you see the manipulation attack. The goal is basically the attacker is the insider. He's the insider, and he can manipulate the update to create a backdoor or to degrade the overall performance. So there are some attack that we call level flipping and others. So what is the challenge to tackle those attacks? So one of the challenges that the server who actually aggregate everything, he doesn't have the original data, client data. He doesn't know that which update is malicious and which update is not malicious. So there is a way to detect that one. Let's say that you can analyze the behavior and then see that which is far from the traditional behavior, but still it's not that easy to find that which is malicious, which are not malicious. So, and you see that they said the filtering approach, adaptive training, accountability, but single defense is not enough. So another attack that we call the privacy attack. Our main focus is basically on the privacy attack because this privacy attack is easy and straightforward. So it can do by the insider or outsider as well. So there are different type of privacy attack that we also see in that additional machine learning model, a membership attack, model inversion attack, and extraction attacks, property inference attacks. So the problem to defend the system from those attacks is that when you have the update, so it seems like innocent, but it may carry a lot of sensitive information about your local data. You don't know that how much information that update carry about your local data. So if the attacker have that update, he may use that update or use that information to recover the private information, or even the attacker somehow can have the access of the model, or if attacker can interact with the model, so there is a chance that he can recover the privacy sensitive training data, let's say that for the medical case. So there are different approach. Some of them use heavy cryptographic approach, but we usually like the non-cryptographic approach, let's say the differential privacy. That is the one of the widely approach that we are also using in this area, but there are a couple of other approaches as well. So this is the overall, that idea about the federated learning. So I think we have 15 more minutes to talk about our contribution in this area. So we have two projects. So one project, we are using the medical data, MRI data to train the federated learning, but our goal is not to train a federated learning model. Our goal is to see that how generative attack or GAN-based attacks can use to recover the privacy sensitive data, and how we can defend that one by using the differential privacy. And second project is to use the resource constrained IoT device. So IoT device, they have the data, but they don't have the sufficient powers to participate in the federated learning. So how we can use them to do the federated learning. In this case, we consider the intrusion detection system. So we face some issue. The one of them is the non-ID issue, the scalability issue, and the privacy challenge. So we'll show you how we deal that one. So can you go a bit from this one?
So the whole idea behind federated learning is that individual clients and even the server does not have access to the private data, the private training data of those clients. But a concept known as model inversion challenges that. It says that given the weights and biases of a model, you can actually reverse engineer it and get the training data from it. So we put that to the test. So we proposed a DC GAN-based model inversion attack for FL systems capable of generating synthetic samples that closely resemble private training data for a specific training class. So basically what he's saying is that our attack will be given a target model with its weight and parameters, and given a DC GAN. So DC GAN falls under the family of generative networks. It is basically a deep convolutional generative adversarial network, which when you train it on a data set, it captures the distribution of that data. So when you give it a latent vector, it can actually generate synthetic images that look very close to the images that it was trained on. So using the GAN and a target model, we have shown that it is indeed possible to recover some of the training images that was used to train that target model. As a part of this research, we have also showed a couple of defense strategies. The most obvious one is we use differential privacy, and we showed that we can mitigate some of the model inversion, some of the effects of model inversion if we use differential privacy. We also analyzed this with different federated learning algorithms to see how different algorithms work in this domain. And we performed all of this experiment in medical MRI dataset.
I think you can take care of the rest. So we are talking about the model inversion attack, but let me explain. We are not the first who use the GAN. In the traditional machine learning, people use the GAN a lot to recover the data. So we just try to apply that one in the federated learning domain. And differential privacy, people use a lot in the different areas. So we just use that one in our domain. The new thing is that we see that there are different aggregation algorithms. So we see the effect of these two things, DGGAN and the differential privacy on those algorithms. And this is the one thing that we see, and another thing that we try to use medical image in this domain to see how to do that one. So, the left figure, if you see the figure in the left side is the traditional machine learning model. Traditional federated learning. We did the federated learning. But the right one is the attack. So in that attack side, we have a pre-trained DGGAN. So why we say that this is the pre-trained DGGAN? So let's say that we have some auxiliary data. Let's say that this federated learning is based on the MRI data. So anyone have the access of the MRI image from the online, and they can use that publicly available MRI image to pre-train a DigiGAN to have some MRI image. But the problem is that that MRI image generated by the DigiGAN, it will not be enough to have the access. Let's say that if the federated learning is the classifier, it will not be, those images will not be enough to be a part of a particular class, because the feature space, there is a feature space, so that feature may not be close to the original features. So in that case, so how the pre-trained DigiGAN actually generate the image is basically from the noise. We call it as a latent vector. So we feed the noise, and the pre-trained GAN can generate the MRI image. But the problem is that to attacking this system, we need to get a feedback from the global model, because global model have the information about the private data that are used to train this model. So this is why we need the feedback from the global model. So in that case, let's say I'm a client, global model provide a service. I can give an image to him as a query, and he can give me a feedback. So in our case, the consideration a bit relaxed. We just consider the loss. So most of the case is said that yes or no, but in our case, we said that let's say that anyhow, the attacker have the access of the loss functions. So he will use that loss function to update his latent vector. So that is the main goal. So if we have the good enough latent vectors, so that latent vector will be sufficient to, that latent vector, if you provide it to the pre-trained DigiGAN, so the image that we generated, that will be sufficient close to the original MRI image that we have. So we'll show that one in the experiment. So if you see this result, the left image, so that are the real MRI image. The right group of images that we see, that are the DigiGAN generated image, but without the feedback. Let's say that is the pre-trained DigiGAN. So it's look like these two images are close, but they are originally not. If we consider it in the feature space, so if I provide that image to the model will classify it as a random class, so because of the feature space. So we need to have the feedback. So this is the feedback that we get, and we have again the image, but in two different conditions. One is the non-DP conditions, and the global model is not trained with the differential privacy. Another one is the global model is trained with the differential privacy. So if you see the top image, that is the original image, and the bottom row are those images that are generated from the DigiGAN based attack, but the global model, they use the different aggregation algorithm. So we see the effect, that how different aggregation algorithm effect on that one to generate the image, but this doesn't give you that much sense. But if you see this distribution, that's going to help you that how close the artificially generated image with the original image. So what we did, we calculate the cosine similarity of the features that the real image and the artificially generated image for the different aggregation algorithm, and we then draw them in the box plot. So we see that not all of them, let's say that some of them almost 80% close. So 80 or 70, above 70% close. But when we see that if we add the differential privacy with the model, then we see that the closeness between these two images, they become less. Okay, so this is the expected, but obviously, so there is a cost related to that one, because if you don't use the differential privacy, you have a chance to get a high accuracy from the federated learning model. But if you added the noise, so we see that around 20% of the performance that are reduced because of the complex data. So this is image data, so we add a lot of noise, so that's why it's reduced the performance. But later we'll see another example. For the IoT data, it will have the less effect. So let's talk about the IoT data. So this is the simple example for the IoT-based ideas. So we don't have the IoT device that don't have the sufficient power. So that's why we bring someone in the middle. We call it as a fog. Let's say the fog have the enough power. So some of the IoT device, they form a cluster and share the data with that fog. And our assumption is that that fog is trusted for this IoT device, but not trusted by the other cluster. So in this case, that fog have those data, and then he use that data to train the federated learning, and he can even include the differential privacy there as well. Okay, so then we did some experiments, and there is one issue that we also introduced, the scalability. Let's say that a group of IoT devices come to the system, how we can use their data and incorporate their data and then added them there. So this is the simple, they can from another cluster, and then there will be a new fog node. He will get the federated learning global model from that server, and then we'll update that one based on that local data. But it's not that straightforward that we said. So we tackle the non-identity, scalability, privacy, and we did some experiments. So for our experiment, we used these two data sets. One is the RT-IoT data, and one is the CIC data. So you see that they kind of, if you see the class distributions, so it's a kind of non-IID. Even we set up a settings in a way that not all client will have the all class data. Maybe some of those client will have the class missing. So based on that experiment, we calculate the performance for the different classes as well as the different client. So we see that all the cases, the performance is above 90%. But some cases, you see the extreme case, there are a few extreme cases, they have the lower performance. So this is the one of the case. Why this happened, I will tell it later, but there is an option that we call it personalized federated learning. So in this case, we can use the personalized federated learning to improve the performance, but still you need to be considered the bias and everything in that case as well. So this is the effect of the DFI. If we add the differential privacy, still we have the high performance. Let's say that only the 1 to 5% degradation. So why this happened? Basically, the data set that we take is not that complex compared to the image data. This data maybe have the 46 features, another one have the 79 features. So it doesn't add too much noise in the system. So that's why we don't see too much performance degradations. So this is the effect of the personalizing. Let's say that the blue line is the initial performance, though these figures show a high performance, but if you estimate the performance of each individual client, you'll see that that performance have a lot of variation. So you need to use the personalized training to improve that performance. That is the one of the way that we can improve the model performance. And there are the few feature directions that we can consider. One of the biometrics, that is the extreme case. So positive class data, only one class data we have. So how to train the federated learning by using the biometrics or behavioral biometrics data, how to make that system scalable. And we also familiar with the multimodal data that have more than one mode. So how we can feed them in the federated learning. And people talk a lot about the large language model. Is there any way to maybe the rack or something? I'm not sure. I'm just trying to exploring that. Is there any way to do the federated learning at the rack part, not the the large language model part? And obviously there is an explainability. So people are working on that area as well. And when we talk about the defense, there are a lot of work that are happening in the defense. But differential privacy, the problem is that when you have a high dimensional data, you need to add a lot of noise. So is there any way that we can reduce the dimension of the data by maintaining the feature or something, not to change the feature that much or something like this? So this is another direction that maybe the random projection, I work on that area that we can use to do that one. So this is the concluding slide. Yeah. So we have the Concordia University, they funded us in our seed program. We started this project not long ago, just 1 year, and we have the couple of collaborators, most of them from the academy, and we need maybe a few collaborators from the industry so that we can apply our research in the real applications. Yeah, that's all about my presentation.
Thank you again for Suraj.
Thank you.